Okay, we're on 5, and 5 is quite a doozy. It's pretty difficult later on. The first one's not too bad. It's just saying consider the function f of x equals sine of p times arc sine of x in the interval negative 1 to 1. Show that f prime of 0 equals p. So first, basically, we're just going to take this function, and we're going to take the derivative of it, right? So sine p, I like writing arc sine as sine inverse. It's a little bit easier, a little bit less writing. So we take the derivative of this function. Derivative needs chain rule, so you start with the outside. Derivative sine is cosine. Once you do that, then you have to multiply by the derivative of the inside. So we have to take derivative of sine. Derivative of sine inverse is 1 over 1, the square root of 1 minus x squared. This is a good one if you don't have it memorized to look up in your formula book and not forget that you are allowed that. And then there's that p in there, so really there's going to be a p up here as well, right? Because of this p being multiplied as some constant. So there's your derivative. We're trying to show that f prime of 0 equals p. So we're trying to say, okay, if I plug in 0, I'm going to get cosine of p times sine inverse of 0 times p over square root of 1, p over 1. So sine inverse of 0, that says that sine of something equals 0. Sine of what gives me 0? For x values between negative 1 and 1, well, that's sine of 0. That's also, yeah, it's sine of 0, right? Sine of 0 gives me 0, and which means that this piece is 0. 0 times p is also 0, so now I have cosine of 0 times p over 1. Cosine of 0 is 1, so I have 1 times p, which is just p, right? So f prime of 0 is just p, right? That's problem 1, problem A, right? A. Here's where it gets a bit complex, right? It says the function f and its derivatives satisfy this mess of a thing. Fn denotes the nth derivative, and f of 0 is basically just f of x. We're trying to show that this here is true. Okay, so this first part's actually not too bad. Just notice what it's saying here, right? It's saying the x value has been replaced with 0, right? And that's the key. Is basically it's saying just show that the n plus second derivative is equal to the nth derivative times this, evaluated at 0. So we need to take this ginormous thing up here and plug in 0, right? So just imagine if you plug in 0 here, and here, and here, and here, and here, what's going to happen, right? So let's think about it. 1 minus 0 squared is 1. So we're left with 1 times f of n plus 2 of 0 minus this x is 0, meaning anything I multiply it by is 0 as well, which means this whole thing here is just gone because I'm multiplying it by 0. It doesn't matter what else is there. And then so that's going to be, that's gone. So then what's left here is we have p squared minus n squared times f n 0 equals 0, right? And that's just the rest of this equation. We're almost there, right? So all we have left to do is, it's trying to show that this is equal to this, which means I need to move this thing to the other side. If I move to the other side, I actually have equals negative p squared minus n squared, because I subtracted it, right? That's how you get it to the other side. And if you distribute the negative, right, it becomes negative p squared plus n squared, which you could just rearrange to make it look like that, right? So that's all that one is. Okay, so the next one is saying Maclaurin series. What you have to remember, the Maclaurin series is basically saying evaluating it as I can write any function as long as I can find its derivatives as the function evaluated at 0 plus the derivative evaluated at 0 over 1 factorial times x plus the second derivative evaluated at 0 over 2 factorial times x squared, plus, in general, the nth derivative evaluated at 0 over n factorial times x to the n. Right, so we need to find what is f of 0. In order to do that, you go up here, you plug in 0, right? So arc sine of 0 is 0. P times 0 is 0. Sine of 0 is 0. So this one is just 0, right? So this function could be defined as 0. This is Maclaurin series, so we could say mx, or m of n. We're going to only go up to like the fifth term, so let's write 5. And that's going to equal, that one was 0. The first derivative evaluated as 0, we already figured out, was p, right? So this is going to be plus p times x, plus the second derivative. This is where it gets tricky. So second derivative, we're going to put it up there. Second derivative, that's where we need this guy, right? This one says the two derivatives forward is the same as the derivative before it times n squared minus p squared. So what we know is that the 0 derivative with the original function was 0. And so 0 times anything is 0. So if this is 0, we also know the second derivative is 0. So this one's just 0 up here. Right, again, that's because we know that if I plug in 0 here for n, this whole thing turns into 0, right? So that one's going to go away. And then here's where it gets a little bit trickier. The third derivative, evaluated at 0. Third derivative is 0, is going to be, let me take this down here, so it's fn plus 2 . Okay, so we know the first derivative evaluated at 0, right? We know if n is 1, we get p, right? So I'm going to go and put 1 in here. So it's 1 minus p squared. And if I plug in 1 over here, then that is 3. Right? If I plug in 1 n everywhere, I am left with I get this, right? So this is the third derivative evaluated at 0, which could be rewritten as that. The fourth derivative evaluated at 0 is also going to be 0 for the same reasoning that this one was 0. So the fourth derivative is just 0, just like this one's 0 and that one's 0. And the fifth derivative, we'll do this again. We'll start out with this equation. In this case, we're looking for the fifth derivative. We know the third derivative, so let's go ahead and plug in 3 everywhere we see n. And then if I plug in 3 over here, I get 5, right? So the fifth derivative is equal to the third derivative times this. This is 9 minus p squared. The third derivative, remember, was 1 minus p squared times p. And so this is the fifth derivative, right? So that's what I would put here, is p times 9 minus p squared times 1 minus p squared over 5 factorial. And then you can see you have the same thing as you have here, right? Then it says, hence or otherwise find the limit of this function divided by x. So we're going to use our polynomial. We're going to use this fifth degree Maclaurin series, right? This thing approximates our function to find this limit. Okay, so we know the top piece. So it's going to rewrite this. We're doing d. We know the top piece. I guess I can just write this so it doesn't get too confusing. We know the top piece at least is approximated by, so I'm going to go and rewrite this as this thing right here, right? So it's approximated by p of x plus p times 1 minus p squared, x squared, no, x to the third, over 3 factorial. This is over 3 factorial plus, and that whatever thing to the x, it's not going to really matter, right? This is all divided by x, right? If I divide all these by x, right, this is going to be p plus p times 1 minus p squared x squared plus blah, 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 x to the fourth, right? And then we're doing the limit as x goes to 0. Using direct substitution, that just means I'd plug in 0 here and 0 here, and I would just, those all go away, and I would be left, I can't plug in a 0 there, so I'd be left with p, right? The limit there is equal to p. So that's one way to find that limit. The other way would be L'Hopital's rule. Let's check that one out. So let's go here. L'Hopital's rule only works if you get indeterminate form. So let's try by plugging in 0 first. If I plug in 0, we already showed that that top piece is 0 in a previous problem, and obviously the bottom piece is 0. So L'Hopital's rule says I can then take the derivative of the top and the bottom separately. Bottom's easy, that's just 1. Derivative of the top is, we did that up here somewhere, is this guy, right? So let's rewrite it as p cosine p sine inverse x, and then over square root of 1 minus x squared, which we can just put that down here, right? Because whatever, when you work that out. No equal sign there. Direct substitution, we know this one evaluated at 0 is p, because we already did that up here, right? We evaluated it at 0. And if you plug in 0 to the bottom, you get 1. And so again, you're left with p. Either way, two solutions, two ways to reach the same solution. If p is an odd integer, prove that the Maclaurin series for f of x is a polynomial of degree p. Okay, so let's think about what p is, right? P is, this number here, which also showed up here, right? And so what we want to think about a couple of things is what happens if n equals p, right? What happens when n equals p? So if n equals p, let's think about what happens to this. Then f of p plus 2 evaluated at 0 is going to equal to p squared minus p squared times f of p of 0. And this would be p squared minus p squared is 0, right? So basically you get that after, like once n is p, right, you might have already found this one, but the next one, right, the p plus 2 one will always be 0, meaning like after p, there are no more terms, right? But again, that's only n plus 2, so you want to think about what the other ones have, but the other ones were the even ones, right? So the even ones are also non-existent 0, which we saw already. So the even ones are 0, and now this one makes sure all the odd ones after p are also 0. Therefore, the last power you're going to have is going to be whichever one was here, right? With the pth power is going to be the last one that's there. That's me just trying to explain it. You can look at the answer key to kind of see some more reasoning and things they did. But that's the reasoning that you can kind of think about is what happens if n is p.